everyone. Thanks for being here. I'm really excited to be talking to you all today about our recent work on identifying a neural biomarker that identifies clinical response after deep brain stimulation for obsessive compulsive disorder. And we did this using continuous recordings in the real world. I don't have any disclosures. Before I start, I want to acknowledge the awesome, fantastic, huge team that Ankit was talking about. We have representatives from neurosurgery, including Dr. Samir Sheth, Baylor Neuro and Rice ECE, Ankit Patel, and psychiatry led by Dr. Wayne Goodman. And I also want to acknowledge our collaborators at the University of Utah, Dr. Ben Shofty and WashU, Jeff Herron. So obsessive compulsive disorder is a psychiatric illness marked by obsessions, which are recurrent distressing thoughts, and compulsions, which are repetitive ritualistic behaviors. OCD can be really debilitating. Many patients experience severe comorbid depression and anxiety and are unable to attend work or school. OCD has a lifetime prevalence of 1 to 3%, and 20 to 40 of OCD patients are treatment resistant. In those 20 to 40% of treatment-resistant OCD patients, we know that deep brain stimulation is a viable treatment option. So in the largest meta-analysis to date done by our group that included 34 studies, 352 patients, 2 out of every 3 patients met response criteria after getting DBS for OCD. And I want to emphasize that these patients were not responsive to anything else that's out there for a very, very long time. So this is really amazing. The conclusion is that DBS produces clinical response in 66% of otherwise treatment-resistant OCD patients. But while 2 out of 3 patients meet response criteria is defined as a 35% reduction in symptom status, which is not the same thing as remission, and 1/3 of patients don't actually benefit at all. So there's still a lot of work that we can do. When we program deep brain stimulation parameters for OCD, the goal of programming is to reduce OCD symptoms without inducing side effects. So if stimulation amplitude is set too low, we still see symptoms, which include distressing thoughts, ritualistic behaviors, feelings of pathological doubt and incompleteness. But if stimulation is set too high, we start to see disinhibited behaviors, which include recklessness, elation, increased libido, and impulsivity. So the goal is to find the sweet spot, which lies somewhere in between these two extremes. But when we place stimulation electrodes during surgery, we actually like to look for some of the acute effects of stimulation. We see increased mood and energy, and here's an example of a video of what that looks like in one of our patients.
Whoa, okay. Yeah, I mean, like an 11 out on a scale of 1 to 10, that was something.
It's good though, right?
Yes, something very good.
What do you feel like doing?
Jumping out of an airplane.
With a parachute?
With a parachute, yes.
And so not only do we see this in the OR, we also see it during the first programming session in the clinic. And here's an example of another patient responding to stimulation being turned on at the therapeutic contact.
That was kind of cool. I don't know, that was a good little jolt. Whatever that jolt was, I like that. Do more of those jolts.
So this is always really exciting to see, but we're really careful when we first program stimulation to make sure that we aren't overdoing it, because we can send patients home in a hypomanic state, which isn't good for the patients either. So right now, the current DBS programming paradigm is open loop, which means the patient comes into the doctor's office, DBS is turned on, and they might say, I think I feel better, and then they go home, they feel great for a little while, over time they might not feel so good, and then they come back and they don't feel better anymore. And so what we're proposing is that remote detection of clinical status could enable data-driven intervention, because this programming paradigm is really high burden, not only for patients that come in from out of state, but for clinicians that have to spend a lot of time with the patients, answering emergency calls, etc. So the goal is data-driven intervention. And so with that goal in mind, we sought to identify a neural biomarker that's predictive of long-term clinical response. Currently, OCD symptom severity is measured by a survey or clinical assessment called the Yale-Brown Obsessive Compulsive Scale, or the Y-BOX, which assesses symptoms over the previous 2 weeks. And our goal was to identify a neural biomarker of response by continuously monitoring neural activity in the real world in the background of everyday life activities. And the real world part is really, really important because 99.9% of life actually happens outside of the clinic. And so we published this work in Nature Medicine in July, and I want to acknowledge my co-first authors, Sandy Reddy and Anthony Allam, who are both medical students at Baylor, and of course Ankit Patel, who was our fearless leader in all of the machine learning and AI aspects. So our hypothesis is that the state of severe OCD, disinhibition, and healthy behavior lie in a continuum, where OCD is characterized by pathological avoidant behavior. Disinhibition can manifest as a side effect of overstimulation, where we start to see impulsive behaviors, elation anxiety, as I mentioned, and healthy approachful behavior lies somewhere in between. And we saw some of that with initial programming. We usually see this where patients are kind of less focused on themselves and more focused on engaging with other people, maybe smiling and laughing more, going after rewarding behavior instead of focusing on avoiding their OCD triggers. And so in order to do this, we had 2 cohorts where we were doing developing our models. Our first cohort, there's 5 patients, 3 responders, 2 non-responders, and we have a very complete data set, meaning data from the moment the DBS leads were implanted and then months following DBS activation. And in our second cohort, we had less data for many reasons, one of which is these 7 patients were implanted later than the individuals in the first cohort. And so in the first cohort, across many of these patients, we saw a spectral peak at around 9 hertz in the power spectral density plot. And this is the frequency range that we decided to track using the Medtronic Percept PC device that can track neural data continuously in a single frequency band that the researcher defines in 10-minute intervals. And so now I'll show you some of the data. I'll show you the non-responders first. So to orient you to these plots, the y-axis is showing time, midnight to midnight. Each column is a day, and the x-axis shows days since DBS activation. So the brighter the color blue, the higher the 9 hertz power, and this is z-scored per day. So you can see that there's this clear circadian rhythm going on where there's a peak sometime in the morning and a trough sometime in the afternoon. And we call this a neural circadian rhythm. After DBS turns on at the vertical pink line, not much changes. This rhythm is very, very stable over time. In our second non-responder in the first cohort, we see a similar effect where there's a clear neural circadian rhythm. After DBS turns on, it's very consistent. We further quantified this as a first pass using a cosigner model. So we fit a cosine function to the data with a 24-hour period. And what these plots are showing is the amplitude and acro phase of the 9 hertz power. And you can see that within the yellow zone of the pre-DBS data where the patient was severely symptomatic, all of these dots are kind of similar to this, are kind of scattered in the same zone. They're all self-similar. After DBS, when symptoms persist, because these are non-responders, there's not much change in the phase or the amplitude of the cosigner fit. So in conclusion, non-responders show a distinct, consistent neural circadian pattern that doesn't change after DBS. But in the responders, we saw something really exciting and remarkably different. Before DBS, it looks just like the non-responders. When the patients were severely symptomatic, there's this characteristic neural circadian rhythm that's really obvious in all 3 of these patients. But after DBS was turned on, we see something amazing. This kind of changes and evolves in a way where when clinical response hits in the blue zone, it looks really remarkably different than it does before DBS. And this held true in our 2 additional responders as well. Again, we quantified it using the cosigner model, and you can see that there's a distinct shift from yellow to blue in terms of the phase or amplitude. So the conclusion here is that in responders, the neural circadian pattern is significantly disrupted after DBS. And so I wanted to visualize this in a little bit different of a way. Here, what I'm going to show you when I play this time-lapse video is 9 Hertz power on this polar plot, so around the clock. So each plot here represents a day. And so in the yellow zone, you could see that it was really lobed and circadian, but after clinical response hits, you start to see this looking really spiky. The neural dispersion is really high throughout the day. It's high entropy. And the way that we quantified this, the feature of choice is we fit a linear autoregressive model to the data and used the model to predict the future points from the past points, computed a goodness of fit, the R squared. And as you can see, when the data becomes really unpredictable after clinical response, the R squared goes way down. So symptom improvement is associated with unpredictable and high entropy theta alpha power over the 24-hour period. And so looking at this a little bit closer, this is just one of our examples from a responder. You can see that these state templates in the severely symptomatic zone are very lobed, the examples that I've pulled out here. And so looking at the model fit, in green on top of the true data in gray, you can see that this is a really tight fit. R squared is really high. After clinical response hits, you can see that the fit is not as good. The green line isn't on top of the gray line anymore. And pulling out this linear autoregressive R squared feature, you can see that after clinical response, there's a significant difference in R squared. So looking at the data from the patients in the first cohort, so 5 patients, you can see that there's a significant difference pre and post response in the responders, but not the non-responders. And when we plot this, just taking the medians of each of those distributions, it's actually separable by a narrow margin. We can draw a line between. So then we submit the paper. The reviewer said, give us more higher N. This is just an N of 5. We need more. And so we added 7 patients, 3 of which came from our collaborators at the University of Utah. And we found that this generalized to the larger cohort, which was really exciting. The effect is more like visually appealing when we take the delta between the pre and post. So that's what I'm showing in the middle column. And here we fit a logistic regression classifier and use that to predict, based on the data on any given day, whether someone was experiencing symptoms or not. And our winner feature, the linear autoregressive R squared, is the dark green line. So we're pretty happy with, I think, an 82% accuracy. So recently, and really excitingly, we heard independently our friends and colleagues at the MGH, Matteo Vissani and Mark Richardson, actually took the code that we published with the paper and applied it to their new cohort of 12 patients. And it's not as clean as our results were. They were tracking slightly different frequency bands, all very close to 9 Hertz though. But when they did that delta and used the same linear AR feature, they found the same thing. There was a greater reduction in R squared in the responders than the non-responders. And they actually were able to replicate our classifier results. And I think their accuracy was actually greater than ours. So that's very exciting. So in conclusion, we identified a neurophysiological biomarker of clinical status after DBS for OCD. This feature is really at the crux of it, neural predictability. The linear autoregressive R squared predicted clinical response. And this generalized to our cohort of 12 patients and generalized to an independent replication in 12 patients at MGH. And we started to think of this feature as kind of indexing where someone is on the approach avoidance axis. So DBS facilitates pro-approach behavior, which may be necessary for clinical response in order to overcome the avoidant phenotype characterizing OCD. And our ultimate goal is to use these biomarkers to enable data-driven intervention, so actually making stimulation adjustments based on clinical status of the patient as measured by on-device neural recordings. And I want to spend my last few minutes talking about how this finding has completely changed the way I think about neural biomarkers in psychiatric disorders and where I think we're going next as a field, what we can do next. So some of you may know about the beta band biomarker in Parkinson's disease. In the DBS world, it's all the rage. It's a really great demonstration. So she's doing this hand open, hands closed task. Right now, she's doing it pretty slowly. I'm sure she was asked to do it as fast as she possibly can. She has DBS in her subthalamic nucleus, and right now it's off. And you can see in the beta band range at about 15 hertz, there's increased power. And so this is a marker of her motor symptoms in Parkinson's disease. Here's another video from the same group, Feldman et al. In Germany. This is Andrea Kuhn's work. So after DBS turns on, you can see that beta band pretty much isn't there anymore. This is like an instantaneous biomarker that with stimulation it goes away and then symptoms are gone. And it's really inspired like a lot of the devices that are on the market that can both record neural activity and stimulate at the same time. And it's inspired like a lot of enthusiasm for closed loop strategies in neurological and psychiatric disorders. So those of us studying psychiatric disorders, DBS, psychiatric neuromodulation, we've been trying to find a biomarker like this for the past 5-10 years. And I'll show you some examples. A biomarker that's immediately responsive to symptom state. So my paper in 2021, in an N of 3, we found that delta band correlated with lower OCD-related distress. Before us in 2019, in an N of 1, Kai Miller and his group found that it's gamma band that correlates with OCD symptoms. More recently, the group at Penn, in an N of 1, found that actually it's all low-frequency bands correlates with elevated OCD obsessions. And in 2023, our colleagues at MGH, in an N of 2, found that it's alpha band. So there's clearly something going on here. It's more complex than just power in a single frequency band that's going to explain OCD symptom fluctuations. And so, maybe we're doing something wrong since we can't really replicate our results across all our groups. So I'm very excited about our results because we have been able to replicate them across a larger cohort. And this result is very different than the way we used to think about things. We're actually looking at variations in the baseline itself as a marker of a slowly evolving state, in this case OCD symptoms or approach avoidance. And so I think that neural biomarkers of slowly evolving clinical states relevant to psychiatric disorders might not actually be episodic variations from the baseline as they are in Parkinson's disease, but rather features of variation in the baseline itself. And I think this theme is picking up a lot of steam. There was a paper in Nature from the Georgia Tech, Emory, and Mount Sinai groups that identified a kind of similar biomarker in a cohort of patients with DBS for depression. They found that this biomarker fluctuated over slow timescales and actually was able to predict descension into a depressive state before the patient was even aware of it. And so, where are we going next? There are currently 2 devices in the US available to do on-device recordings during stimulation, the Medtronic device and NeuroPace, but there's actually more and more of these devices being developed all over the world. And we can start pairing these devices with behavioral data coming in from wearables, including the Apple Watch and iPhone, the Whoop Band, Oura Ring, Dream Headband, Fitbit. And ultimately, our goal is to use these neurobehavioral readouts, continuously monitor them while the patient's at home, send the data to the cloud, the clinician can see it, and they can make a decision about what do they want to do. Do they want to change stimulation settings? Do they want to bring the patient in, call them, see how they're doing? And if it's a stimulation change, then hopefully they can automatically implement that and deliver that to the patient. And so with that, I want to thank my growing lab at Baylor, and thank you for your attention.
We have definitely time for few questions. Alex.
That was super cool. Thank you. So I'm interested, this 9 hertz oscillation, like what is that? It's not alpha, it's not theta. You called it like alpha theta. Where does it come from?
Yeah, so I get this question a lot. It's a great question. I don't know. So we do sometimes see a peak in the spectrum there, which is why we ultimately decided to record there. But, you know, sometimes that peak isn't there. So what the device is measuring is average power in the band that I define, regardless of whether it's like a deviation from the 1/f, like aperiodic background activity. And so I think primarily probably what we're measuring is actually just background activity. I don't think it's an oscillation. And so like one thing I'm really interested in exploring in the future is like, and my guess is many low frequency choices would yield the same result. But you know, we'll have to get the data and see.
Other questions? Oh yeah, Roy, you've got to wait for the speaker, for the microphone.
I guess like the other answer to this is 9 hertz is like at the border of alpha and theta, and like we do care about like inhibition and like response selection, kind of cognitive control, and both of those frequency bands are related to that. So those might be like relative cognitive constructs to track for like this approach behavior that we're interested in.
Thank you for the talk, and I apologize if I missed this during the presentation, but I'm curious whether the biomarker you found, I guess, measured the extent of the symptoms as well. I understand that it helped to classify in a binary manner whether subjects responded, but I'm curious if it also measured how well they responded.
Yeah, that's a great question. That needs to be our next step, exactly that. So right now, like clinical response is kind of, well, we binarized it, right? Either the patient's a responder or not a responder. And part of the reason why we did that is we don't have that many touch points with the patients to get these clinical assessments. So how I think we can do this better is by using wearable sensors. We've started doing this with Oura Ring to monitor activity and sleep. A lot of times patients are housebound before DBS, but move around a lot. After they start getting better, they leave home, they go back to work, all those things. And so I think having like an objective behavioral readout would help us to figure out where someone is on that spectrum. I can probably, let me go back to this slide. So I love like this top patient's data because between yellow, which is severe symptoms, and blue, clinical response, you can see that there's like kind of this evolution of neural activity happening where right after DBS turns on, the circadian rhythm like hangs on quite a bit. And then it kind of like evolves into what it looks like after clinical response. So I think that based on just visual inspection, it looks really promising to be able to like figure out exactly like what is the trajectory of clinical improvement.
Great, thank you. And then as a follow-up, I'm wondering if you also expect, you mentioned that with too much stimulation, you may induce hypomania in some of these subjects. I'm curious if you anticipate this biomarker to also measure that if it gets too far beyond the clinic.
Yeah, I thank you for asking that. I am very excited about that as well. This might take too long to go. Oh, no, here we go. So we originally actually did include this in this paper where we were trying to say something about the disinhibited periods, which are actually labeled in red here. The P005, the patient on the bottom, is a good example of that. What I think happens during disinhibition is the circadian rhythm like kind of completely goes away, and there's really not much variation. And that's kind of what you see here. Like immediately this light blue turns dark, there's nothing going on. But our N is like the number of days we have when people are hypomanic, thankfully, is very low. So we couldn't really statistically say anything about that.
Thank you.
Thank you. Thank you, Nicole.